Hello everyone. This is my presentation on the problem of graph non-isomorphism. Firstly, to define graph isomorphism, we can say that two graphs G and H are isomorphic if the nodes of G can be reordered so that it is identical to graph H. You can see this formal representation of the isomorphism problem. And if you look at the example, the graphs G and H look very different at first, but if you draw a graph G with the isomorphism, you will see that they are actually identical graphs. And the formal definition is two graphs G and H are isomorphic if there exists a matching between their vertices, such that two vertices are connected by an edge in G if and only if corresponding vertices are connected by an edge in H. As you can see, graphs A and B are isomorphic, and graph C is not. The graph isomorphism problem is in the NP class of problems, meaning that it is possible to be solved in polynomial time using a non-deterministic Turing machine. However, there are no known polynomial time algorithms for this problem, nor a proof that it is NP complete. The language complementary to isomorphism, named non-isomorphism, can be represented as follows. Basically, just the same as iso, but the two graphs are not isomorphic. This is not known to be in the NP class, as we do not have any way to certify that two graphs are not isomorphic. So how can we go about solving the graph non-isomorphism problem? The answer lies in interactive proof systems. Interactive proof systems provide a way to solve problems in NP with a high degree of, but not absolute certainty. Languages in NP are those whose members all have short certificates of membership that can be easily checked. An interactive proof system breaks this idea into two entities, a prover and a verifier. The prover's job is to find proofs of membership, and the verifier's job is to check these proofs. The verifier must be bounded by polynomial time, otherwise it couldn't verify the answer. There is no computational bound on the prover. A simple example that illustrates the power of interactive proof systems is the satisfiability problem. To solve the satisfiability problem, a prover can convince a verifier that a formula is satisfiable by supplying a satisfying assignment. However, could the prover convince a verifier that a formula is not satisfiable? It turns out it can if the system is given two additional features. First, they are permitted to engage in a two-way dialogue. This means they can send information back and forth for a set amount of steps. And second, the verifier may be a probabilistic polynomial time machine that reaches the correct answer with a high degree of certainty. We can use an interactive proof system for the graph isomorphism problem like this. Given two graphs, G1 and G2, if they are isomorphic, the prover can convince the verifier of this by showing a reordering of one of the graphs that makes it equal to the other graph. And then the verifier could verify this fact. But if the graphs are not isomorphic, how would a prover convince the verifier? It is not enough for the prover to declare that they are not isomorphic. The prover must convince the verifier. This leads to the following protocol. The verifier randomly selects a graph from the input and reorders the nodes to obtain a graph H. The verifier then sends this graph to the prover. The prover must respond by declaring which graph it thinks was the source of H. If G1 and G2 were non-isomorphic, the prover could always complete the protocol because the prover could identify whether H came from G1 or G2. However, if the graphs were isomorphic, H could have come from G1 or G2. This means that even with unlimited computational power, the prover only has a 50% chance of choosing the correct answer. Therefore, if the prover is able to answer correctly consistently, maybe 100 repetitions of this protocol, the verifier has convincing evidence that the graphs are non-isomorphic. Next, we move on to defining the model, starting with the verifier. The verifier can be defined as a function v that computes its next transmission to the prover from the message history up to that point. V has three inputs. Firstly, it has an input string. The objective is to determine if this string is a member of some language. For the graph non-isomorphism problem, the input string consists of two graphs. Next, there's a random input. The verifier is provided with a randomly chosen input string so that it can make probabilistic actions during computation. Finally, it has a partial message history. V itself has no memory of the previous dialogue, so a string representing the exchange of messages so far as sent. This is of the form m of 1, m of 2, all the way to m of I. The verifier's output is either the next message m of I plus 1, or accept or reject. You can see the functional form of V below. The statement V of W, R, m of 1 to m of I equals m of I plus 1 means that with input string W, random input R, and the current message history, the next message to the prover is m of I plus 1. Next, we can define the prover. The prover is a machine with unlimited computational power. It is defined as a function p with two inputs. Firstly, the input string, which is the same as the verifier, and the partial message history, which is also the same as the verifier. The prover's output is the next message to the verifier. P has the functional form shown below. P of W and the history equals m of I plus 1 means that the prover sends message m of I plus 1 to the verifier after I messages have been exchanged. Next, we define the interactions between the verifier and the prover. For particular strings W and R, we write that an interaction between V and P given W and R equals accept if a message sequence m of 1 to m of k exists for some k whereby, firstly, for 0 less than equal to I less than k, where I is an even number, V of W, R, and the message history equals m of I plus 1. Second, for 0 less than I less than k, where I is an odd number, P of W and the message history equals m of I plus 1. Basically, these first two rules clarify that it is a valid interaction. It goes from the verifier to the prover to the verifier and so on. And finally, the final message m of k in the message history is accept. To simplify the IP, or interactive proof class, we assume that the lengths of the verifier's random input and each of the messages exchanged between the verifier and the prover are p of n for some polynomial p that depends only on the verifier. We assume that the total number of messages exchanged is at most p of n. The probability that an interactive proof system accepts an input string W of length n can be defined as the probability that the interaction between V and P accepts W equals probability that the interaction of V and P given W and R equals accept, where R is a randomly selected string of length P of n. Next, we can define IP space. A language A is an IP if some polynomial time computable function V, the verifier, exists such that for some arbitrary function p, assumed to be an honest prover, and for every arbitrary function p1, assumed to be a dishonest prover, and for every string w, W being in A implies the probability that an interaction between V and P except W is greater than 2 over 3, and W not being in A implies the probability of an interaction between V and P of 1 except W is less than or equal to 1 over 3. In other words, if W is in A, then some prover P causes the verifier to accept with a high probability, in this case 2 over 3. But if W is not in A, then no prover, not even a dishonest prover P1, can cause the verifier to accept with high probability. We can increase the number of repetitions to make the error rate exponentially smaller. For example, we can run the non-ISO protocol 500 or 1,000 times to virtually guarantee a correct answer. Now we can run through some examples of our interactive proof system. Given two graphs G1 and G2 that are non-isomorphic, we input these into our interactive proof system. First, the prover claims that G1 and G2 are non-isomorphic. The verifier then selects a graph and applies a random permutation, then sends it to the prover. Upon viewing the permutation, the prover selects the correct graph and sends its answer to the verifier. The verifier and prover then repeat steps 2 and 3 for 10 iterations. Because the graphs are non-isomorphic, the prover is able to answer correctly every time. The verifier now has proof that G1 and G2 are non-isomorphic. This is because if the prover was guessing every time, the chances of choosing the correct graph 10 times in a row is 0.5 to the 10th power, or 0.098%. When the verifier is satisfied in the proof, it can accept the prover's claim and state that G1 and G2 are non-isomorphic with a probability of 99.902%. Now an example with isomorphic graphs. Given two graphs G1 and G2 that are isomorphic, we can input these into our interactive proof system. Firstly, the prover claims that G1 and G2 are non-isomorphic. Then the verifier selects a graph and applies a random permutation, same as before, then sends it to the prover. Upon viewing the permutation, the prover guesses a graph, because either graph could be the origin, and sends its answer to the verifier. But it turns out the prover's guess is incorrect. This tells the verifier that G1 and G2 are isomorphic, because if they were not, the prover would be able to distinguish between them 100% of the time. The verifier knows that the prover guessed, meaning that the graphs have to be isomorphic. The proof is concluded at the first incorrect guess by the prover. The verifier now knows that G1 and G2 are isomorphic and can reject the prover's claim. However, there is a chance that the prover could guess correctly for a number of trials, which highlights the need for repetition. And that concludes my presentation on how we can solve the graph non-isomorphism problem with interactive proof systems. Thank you for listening.